This is basically an effort, a fundamental project, an effort to realize a primary resistance standard using the quantum anomalous Hall effect. So we already had a kickoff meeting at CMI. It's a team effort, so most of the team is here, but almost all of them. Yeah, so the overview of the presentation is basically a bit protracted because first I will give you the need, then quickly breeze through quantum Hall, and then focus a bit on quantum anomalous Hall and material, different types of material focus there. Then I will introduce the project and the type of materials that we'll be using in the project. Then I will give you context with respect to what is happening outside of Europe and in Europe, what has been happening, and then quickly give you an insight into what kind of setups we have, what kind of work has already been done on a parallel project, which is now overlapping with this project. So the idea is that, like Frank said, so we want a quantum current source. So or what you would call a quantum electrical metrology toolbox, where you have in a single cryogenic system both the Josephson voltage and the resistance standards sitting. Gallium arsenide technology has been robust, but it's starting to get old. It is being replaced now. We are now in the graphene age, and now we need to start thinking about next steps, what goes beyond graphene, because now if you see, it's just incremental improvements that are happening in graphene, not a shift. So we need to think about how we can move from the existing physics that we have and we have understood to new type of physics. What really changed the game was the discovery of topological quantum materials, because topological insulators that allowed us to study unique material properties, taking advantage of the field of topology in mathematics, which allows you to have protection from any kind of defects on the surface state, that is where the electron is passing through. But as with all new technologies, there are limitations. So limitations here is operating current and the temperature at which this phenomena of quantum anomalous Hall is observed. So in this process, we decided that we will write this project and we will give basically starting threshold that we will achieve zero magnetic field quantization. And this will be realized above 1 Kelvin and in currents greater than 1 microampere. So it's easier said than done. It's a pretty difficult thing to achieve. So quantum Hall effect, basically it's number 2, but it should be number 1, my mistake there. So it basically works as you have a 2-dimensional electron gas, you apply a perpendicular magnetic field, you have, when you apply that, you have the gauge field which couples to the electron momentum. So you have the bulk localized, you have edge states that are moving around. But in order to achieve this, you need high mobility systems. You need high mobility samples. 2 dense, very good. And then comes graphene as well. Here you really have to basically tune the charge carriers and the mobilities, etc., to achieve very good quantization. This is more of the recent papers from PTB, where they played around with the graphene and they doped it P-type and N-type, and they were able to show very good quantization. As you can see from the values, enough for DIPM to actually consider seriously. Also preparing a transition from gallium arsenide to graphene standard. Which is amazing, the next step. But now that we have reached this point in graphene, we need to think of the next step beyond that. In comes quantum anomalous Hall effect. Now, quantum anomalous Hall effect doesn't do with gauge field, it does with exchange field. So what it does is you have basically a Dirac system, which you can see here, with a Fermi level sitting in the middle. Ideally, if you were to break this, which conserves or preserves time reversal symmetry. So in order to see any unique phenomenon, you need to break the time reversal symmetry. You can do that by applying magnetic field. Of course you can. But what you can do is you can also use different techniques such as magnetic doping or proximity coupling to spontaneously break time reversal symmetry. So spontaneously means then you do not need to apply a magnetic field. It just breaks time reversal symmetry by itself just because the magnetic species is present. And these are pretty large fields of almost 100 Tesla, and which is pretty robust. And the quantization level is 1. These are also called Chern insulators. Quantum Hall effect is also a Chern system. And this is Chern value 1, whereas in quantum Hall you generally have a value of 2, the plateau that you take. So this is basically 25.8 kilo ohm value that you are focusing here on. Now, the anomalous Hall and the quantum Hall the anomalous Hall and the Hall effect were 2-3 years apart, done by Hall. But it was only in 1980, 1985 when we got the quantum Hall effect. But it took a few more years, and it was the first realization in 2013 of the quantum anomalous Hall effect. This was done in magnetically doped bismuth selenide telluride system, and it was achieved at a temperature of 30 millikelvin, pretty low. But it was pretty robust when the temperature is maintained. Then people started to really play with different types of doping, and you can see here CDST, BBST, modulation dope. These are all unique ways of doping that were achieved. Say, chromium is used in America quite a bit, chromium doping. Vanadium is predominantly how it is done in Europe. That's how we do it. And modulation doping is what is done quite a bit in Japan. Just different flavors, same principle. But there are other pathways as well. So what I talked about is the first one, doped topological insulator. But you have other species that are intrinsically magnetic. I will not go there. It has to do with the periphase and pericurvature. I will keep that out of this presentation. And then you have basically topological insulator sitting on top of a magnetic insulator. So that also can break through proximity effect time reversal symmetry. So here is the example of how heterostructures are created, where you can play around with. This is European sulfide bismuth system, topological insulator that was studied. And as well as the thulium iron garnet, which is one of the samples that we'll study in our project as well. There are other paths as well. You can do it with twisted bilayer graphene. It has also shown plateaus, quantized plateaus, not so well, but at high temperatures of 1.6 Kelvin, which is pretty promising. And then you have these antiferromagnetic flakes of manganese bismuth telluride, which also show quantization. Other possibilities exist for such magnetic topological insulators, more exotic phenomena. Most important of all for physicists is the topological magnetoelectric effect, which is pretty promising in terms of application, future applications. So coming to the project, so all of this effort, all this science led to this point where we decided to form a consortium of 14 partners distributed in Europe and Japan. We are a healthy distribution of 7 NMIs and 6 research institutes to carry out fundamental aspects of fundamental studies. This is a big one because these are the objectives. So the first objective, we are focusing on two parts. One is the established one, magnetically doped systems that have shown very robust quantization, but they are at very low temperatures. In order to increase the temperature, we need to go with different unique new materials. So the objective first one, we would be exploring different types of anisotropic magnetic insulator layers and new types of materials which are called Kagome systems. We will characterize them. So this is basics science physics, where we characterize them in detail from starting at room temperature all the way down. We would also use scanning probe microscopy to study these systems, which is not so well established, not so common. So we are hoping for very promising results using scanning probe techniques, which are like 3-4 of them that we'll be using. And then finally, the fourth objective is where we'll do metrological characterization using a cryogenic current comparator. And of course, all these development of technology and measurement infrastructure, we will be helping or working with BIBM for uptake. Workflow is pretty simple of this project. We have growth of the materials, which then provides samples to work package 2 property characterization. It's a feedback loop. We have three rounds of feedback if the material properties need to be optimized. Same goes for work package 3. Precision metrology, if we find that there is something, some material issues that can be reverted back to work package 1. And all of this leads to impact, which is INRIM's responsibility. There are 4 expected outcomes. Currently, there aren't enough NMIs having the capability to carry out such research. So we want to develop these capabilities to do this. Also to fabricate and characterize topological insulators. These are new type of materials, so we need to do that. We'll also be developing a good practice guide in this, and of course, the knowledge transfer. Like I said, 3 types of materials that will be studied. One will be the workhorse, the first one, magnetically doped topological insulator. The other 2 are exploratory, high risk, high reward. Okay, coming now to what has been happening across the world. This is the first result which in resistance metrology people would be aware of. This was a work done between Weekend and NMIJ. What they did was they prepared a stack for quantum anomalous Hall, and they placed a permanent magnet on top of it. And they achieved through this quantization, and they measured it sitting up here and having a quantum Hall, a gallium arsenide quantum Hall system sitting in magnetic field down here. So they compared the results, and they got a 10 parts per billion Hall resistance, but in a magnetic field of 0.2 Tesla. Stanford also worked with NIST in the US, and they carried out their system using chromium dope topological insulators. And later on in 2023, they tried to create a quantum current source. This paper has not yet been accepted. We are still waiting for the modifications, and we are waiting for the paper to come out, and let's see what happens here. Here they used a quantum anomalous Hall in tandem with a Josephson system in a single cryostat. And they achieved a QCS range around between the nanoamp and microamp range. In 2018, in Europe, University of Würzburg and PTB published their very early results on quantum anomalous Hall. It was not the best, but it was not bad at that point. It was pretty early on, so 10 to the power -6. But since then, they have the Würzburg group has improved their growth process and the characterization and the fabrication processes. So here you can see the Hall bar device. This is the stack that is used. So basically, the magnetically doped system is vanadium is doped here in BST. And this is the device when it is placed on a DO8 sample holder head, I believe. These are the results that came out. You can see the beautifully quantized step there at zero magnetic field. There is absolutely no magnetic field here when it is quantized here at 5 nanoamperes and 5.8 volt of gate voltage. The temperature is 34 millikelvin. This paper is basically showing you. You can have a look at it. It's on archive, and it was recently accepted in Nature Electronics. They did a different terminal check of these devices, and they came to within 10 to the power minus 9 or ppb level accuracy with no magnetic field applied. So this is the paper. You are more than welcome to have a look by yourselves. And this is basically what was done in a European FET open project called TOCHA. And this is where we enter into the QuAHMET project at this stage. The project will use, as I said, scanning probe techniques to study different kind of states, how they look like, so imaging. And current flowing imaging, that is also very important to understand how the current flows in the system and how the magnetic domains are spread out on these. So we have NPL, Metas, and Univas providing these input. Then we have pre-characterization at helium-4 up to 300 millikelvin, helium-4, helium-3. And then dilution systems at these NMIs and universities. And eventually there will be CCC systems used at all these NMIs and the university to carry out precision measurements. This is kind of the SPM setup for very low temperature studies. It kind of looks similar to what you would see in a dilution fridge, just that it has different servo motors, etc., for moving X, Y, and Z direction at cryogenic level. All these measurements have to be characterized at higher temperatures. So you have test probes sitting here that the lab at the University of Basel does pre-characterization before they introduce it into the dilution fridge. And then you have an example of the setup, which is present at PTB, how it looks like. The old top loading system, they're bringing in a new one. I think it is more or less done or about to be done. Hans, you can let us know. And the very recent results also provide us with a promising path. Apart from temperature, we also have currents above 1 microamps. Everywhere we're using nanoampere currents. So the Würzburg group came up with a fun way of creating, instead of a Hall bar geometry, they used Corbino geometry. And then they use a technique called balancing technique, which, as you can see, allowed the system to work beyond 1 microampere already. So this will be further improved in the QuAHMET project, and we are hoping to most definitely achieve currents above 1 microampere. So the only limiting factor right now in the QuAHMET project is the temperature, which is not going to be so straightforward. That's the status of the project. Thank you for your time.